All right, good morning, everybody. Welcome to the reinforcement learning and control session. So this is going to be short and sweet. It's going to be 5 talks only, so it's going to be like very refreshing after all these very long sessions. So the first speaker is Max Simchowitz. He's going to be telling us about his results with Ross and Beck. Yeah, thanks.
Hi, everyone. So I'm Max. I'm a PhD student at UC Berkeley. I'm going to talk about some work with my colleague Ross, sitting here, and Ben, our advisor. So linear dynamical systems, they've become a really popular class of models to study in recent years. Just a refresher, so the way that they work is that you have a set of states, and they evolve linearly in past states, as well as inputs, which you get to put in. In our setting, you don't get to see the states directly, so there's an observation model which is linear in the states as well as the inputs, and we'll call these the outputs. So for our purposes, the states are hidden from view, but the inputs are something in our control. And we're going to use our control over the inputs to learn a mapping, to learn the relationship between u and y. So specifically, we want to estimate the parameters of the system, a, b, c, and d. And if you get those, you can do tons of cool things. It's a fundamental problem in control theory because you can do control, estimation, filtering. So that's our goal. Now, in our setting, we also have noise. So we have sensor noise, which affects the output. And perhaps more pernicious, we have process noise, which actually affects the hidden state. And we're actually going to make our results hold with very few assumptions on these, even if they're sort of adversarially chosen, our results go through. And kind of as learning theorists, we want to understand what's the thing that makes this problem easy or hard? Like, what are the fundamental quantities that govern the challenge of this sort of problem? So the kind of conventional wisdom in this space is that learning is hard if correlations decay slowly with time. So the way that we can visualize that is I'm going to plot the eigenvalues of A. I'm going to assume that they're less than or equal to 1, and I'll plot them in the complex plane. One key difficulty is that A often has complex eigenvalues. And the radius of the smallest circle that contains all these, or equivalent to the largest magnitude eigenvalue, is called the spectral radius of A. And it has a nice operator theoretic interpretation, which is this sort of limiting process over here. And the intuition that you should have is this is going to describe how fast excitations in the system accumulate. So what I mean by that is, if I write out the recursion, which takes all the past inputs to past output in the absence of noise, I see this dependence on powers of A. And if the powers of A decay quickly, i.e. if the spectral radius is small, then I have a dependence on few past inputs, and so excitations aren't going to accumulate too much. Another perspective is this is also how fast the correlation with the past inputs decay, because if A decays quickly, I only depend on the most recent terms in this sum. And so there are also limiting cases of this. So for example, if the spectral radius is equal to 1, I have no correlation decay. The effective past inputs remain residual, and we're not going to think about the case where spectral radius is bigger than 1, where things just blow up. But kind of the important part of this perspective is that this is saying that this edge case is actually the really difficult, challenging thing to deal with. And we want to understand, is that true? Is that really fundamental? And the reason we might even care about this edge case is there are lots of interesting problems that start to live in this regime. For example, Newton's laws, classical mechanics in the absence of friction, actually go up to the spectral radius equals 1 case. So this would kind of paint a very damning picture of learning for Newton's laws. So yeah, that's the purpose of this talk, to understand, is this the correct picture? So what I'm going to do first is I'm going to explain kind of the least squares approach to learning these problems. This is a framework due to Oze and Oymak, and it's also kind of been studied classically for years now. So here's a linear system. I'm going to define this matrix. I'm not going to go into too much detail what it is, but it's called the Markov matrix. And kind of the useful thing about it is that it gives a response, a noiseless response from inputs to outputs. So what I mean by that specifically is if I were to take a vector of concatenated inputs going from 1 to k, then the Markov matrix would give me the exact response from those inputs to the kth output, right? So it's kind of just this linear process, or linear map. And the nice thing that we can show is that if I recover this matrix G star, then I can recover all the system parameters that I wanted to get. And in fact, this also holds approximately. So if I have some statistical error, that translates into this. And there have been refinements of their result that have done better, get better relations between the error of one and the error of the other. So our goal is going to be to recover G star. So now we're going to introduce an important error decomposition that facilitates our analysis. So again, here's our system. I've added noise back in so we remember what it is. Here's length k history, so I'm going to imagine a u bar t denotes the nth input down through k, minus 1. And there's a nice relationship that we have where the output is linearly in u bar t plus some error term delta. Obviously, this equation is always just generic. But the important thing is that this delta, this error, it actually only depends on past inputs as well as the noise sequence. And in fact, on noise that also comes sort of from the past. So on the other hand, what we're going to do is we're going to choose the inputs to be Gaussian white noise. And the important thing about having this sort of past relationship with delta and the white noise inputs is that we get the following identity, which is that the inputs, this concatenated sequence of inputs, and the noise are uncorrelated, conditioned on the past. And of course, you make this precise with filtrations. But the nice thing about this is that this is actually sufficient to get consistency of least squares in many regimes. It's known as a semi-parametric relationship or a Nyman orthogonality, and it's been really popular in recent years, and similar things have been studied by this year's best paper. And so, yeah, it's enough to get consistency of least squares, and which is kind of nice. It also actually allows us to deal with adversarial noise. So we don't need to assume, for example, that WT or ZT are unbiased. They could be some random process chosen beforehand, which is really useful. So let's just go through an analysis of least squares really quick and see what happens. So here's a relationship. Here's a least squares estimator. I'm just going to pick the G that minimizes square residuals. And what we prove is, for least squares, you get the following rates. So let me unpack this for a second. Square root dimension over n, I won't say exactly what dimension is here, but that's the standard thing that you should expect from a least squares analysis, right? So this other term might be a little bit more mysterious, but you should think of it as a variance term. So what it is it's the operator norm of the matrix consisting of all the errors delta, t, and it's normalized by square root n. So for a sense of scaling, how big is this? Oh, there's also a cool chaining idea in the proof that you guys should read if you're interested. Think of this as order 1 if all the delta t's were sort of magically white noise. And the reason for this is that sort of each delta t will be of constant magnitude. You'll have a matrix of n entries, and its operator norm will be square root n. A similar argument shows that if A star is strictly stable, if the system is strictly stable, then also this thing is going to be order 1. But unfortunately, this constant is going to get worse and worse as the system becomes less and less stable. The errors are going to accumulate because they depend on the inputs of the past. And in fact, you can prove that least squares becomes performance degrades and becomes worse and worse. And in fact, for marginally stable systems, you're not even going to get consistency anymore. So the question is, can we do better? Is there a better approach? So pre-filtered least squares is our way of getting around this. So what I'm going to do is imagine the thought experiment where I could predict the errors. So I'm going to consider linear predictions of the errors, where I've got something called a filter, just a linear map, and I have features kt. These are the features that we use, but the thing that you need to, the kind of crucial thing about the features is just that they need to come sufficiently from the past for things to work out. So don't think too much about the specific form here. And what we're going to do is we're just going to choose the best filter in hindsight according to our data. So choose the thing that predicts the YTs. It turns out predicting YTs is basically the same thing as trying to predict the errors, even though you can't see the errors directly. And then we're going to use this best predictor, and we're just going to subtract it off from YT. So you should think of this as like a denoising step. We're just trying to remove some of this noise. And you're going to train least squares using the best filter. So this is the algorithm. And what we're able to show is a really nice Oracle inequality for this, which says that basically we get the same least squares rate, square dimension over n, slightly different dimension term. But now the variance term is replaced by this optimal term, and I'll explain exactly what it is. It refers to the best prediction possible of the errors, the best prediction delta t over all possible filters. This is actually kind of cool because this is data dependent. So if you had a semi-adversarial sequence being chosen, it'll adapt to what the adversary did in hindsight, which is kind of nice. And it represents sort of how well an Oracle looking back at the problem would have done for filtering the error, which is really cool. And it can do a lot better than least squares, as we're going to see. So last bit of the talk is just to talk about how small is this opt term. So what we show is that for any system where the spectral radius is less than 1, you can always bound this opt term normalized appropriately by a constant, which is really cool. And in particular, combining with our theorem, it implies that you always get this 1 over square root n rate, and you get consistency for systems of this form. Now the question is, what is this constant? We set out to figure out what makes these problems easy or difficult. And we introduce a new notion of complexity called phase rank to kind of measure sort of how big the error is induced by trying to filter optimally. And I'm just going to touch on what phase rank is. So roughly speaking, phase rank is a more refined covering notion than just spectral radius. So spectral radius is the smallest circle that'll contain all the eigenvalues. Phase rank is the number of ranks, number of spokes needed to cover eigenvalues according to certain geometric rules, which we won't have time to talk about today. But basically, it's related to canceling poles of a minimal polynomial, and it kind of relies on these like approximation theoretic ideas. And it's typically small, so for systems that are real diagonalizable, it's at most 2, and in many cases even just 1, though our dependence on phase rank is exponential, so we do want it to be very small, but we think that it might be unavoidable to have a polynomial dependence on phase rank. And the idea of phase rank here, because it's about canceling polynomials, you can think of it as replacing properties about estimation with properties about filtering, about what you would do if you knew the system and you try to do prediction in a known system. And kind of here's the key takeaway at the end of the day, is that correlation decay is not the intrinsic measure of complexity, and that perhaps these notions of filtering and debiasing and denoising are. And so that's the result. Cool. We don't have lower bounds. Yeah, it would require really complicated packings of these things, which is just, prior work has lower bounds when you get to see the state. But for hidden, it's a little trickier. It'd be really interesting. If anyone wants to prove lower bounds, please do it.
So in the algorithm, do you use any resets or anything?
No resets, just one step. The kind of key thing to keep in mind is that the debiasing step, it's not a debiasing step, it's a denoising step. So you're already going to get unbiased estimates, you just need to reduce the noise, in contrast to normal semi-parametric statistics where you actually need to remove the nuisance parameter. So that's the kind of key thing to keep in mind. Okay.
Okay, let's thanks again.